Hello, everyone. My name is Cary, and good morning. And thank you guys for coming this morning to my talk about Global Unique Index, a different approach. So it's about time we get started. So just a little agenda for today. So I will speak a few words about me, and basically it's my first time giving a talk in PGCon, and actually it's my first time in PGCon as well. So we'll talk about the global index and just where it got started, the background information and its benefit and the drawbacks. So this is from the community discussion back in 2019. So this is actually where our work got inspired from. And then we will start talking about the global unique index. So you will notice there is some difference in terminology, and I will explain that why that is there. So we'll talk about our approach and the syntax that we introduced, how it works, and some benchmark numbers. And in the end, we will talk about the problems about locking, and there are some performance issues with it. So this is not a completed feature, and rather is still open for different better ideas, and is still being in development as well. And then I will give you a summary and the related links where you can see the original email thread and maybe some blog post about the both approaches. So just a few words about me. Since it's my first time here, I think I will just give a little introduction. I'm a student at UBC. I graduated from the electrical engineering department back in 2012. And after graduation, I started working at a software company, working on smart meter innovations, like the smart meters that you have in your houses, electricity readings and stuff. So I joined Heigl Software in 2019, and that's the time when I started my postgraduate journey. So I'm still very new to this space, about 3.5 years until now. And so this is where I began this journey. And the stuff I'm mainly working on includes the sharding, enhancement, distributed database. We have some work on that too. High availability, some deployments related stuff, and some shared storage and also security. So that's basically the area that I spend the most time in. Okay, so I also a postgraduate instructor at the Peking University, I think back in 2021. And it's about an open source project. So of course, I use Postgres as an example to get the students involved in the PG, the community. Yeah. So let's talk about the background, where EO came from. So it's proposed back in 2019 with this title in the hacker email thread called Proposal Global Index. So basically, if you look at the diagram on the right here, so a regular index looks like this on the top right corner. So each partition table and your partitions have a index associated with it. So you can call this a partition index as well. So it shares the same structure. And the global index in this proposal is trying to kind of do something like on the top bottom right corner here, where you will have a single index relation that kind of reference to multiple partitions. And to achieve that, the single global index has a heap OID as a reference. So this is one big relation that has multiple partitions, index tuples. So we can understand it like that. So it's a one-to-many relations. So it's kind of combine everything into one. So that's the idea. And there's some benefit with this. You can achieve a cross-partition uniqueness because you don't have multiple partitions now. You have everything in one place. So automatically you can create a unique index, and it will apply to every partition that exists in that global index. And there is some performance increase. Because of the global index, you do not need to do a index scan when you do your select query per partition. So there's a less scanning happening because you don't have one, even though it's a big one. But you save a little bit of overhead when you want to switch scanning each indexes for each partition. And the main performance gain actually comes from the last benefit, which is the partition keys are no longer required to include when you are creating a unique index. So in the regular PG with the regular partition table, when you create a unique index, it will require you to include partition keys because it cannot guarantee the uniqueness across other partitions. So having that in there, because partition keys is always unique, it kind of makes sense there. But in global index, it's no longer required, so you don't no longer need to have a multi-column index. And with that limitation lifted, there's a significant performance increase with your select. And we'll talk about the numbers after in the later slides. So let's talk about some drawbacks here. Yeah, it sounds good. Okay, you get global uniqueness check and you have some performance gain. It's great. But in order to achieve that, you need architectural changes. And by that, it will involve changes in the planner, in your optimizer, in your executor. And most importantly, it will affect the partitioned infrastructure. Because we have partition table for a reason. We want to break down a large table into a smaller chunks for easier management, easier access, and faster lookup. But it kind of contradicts that purpose by putting it all together again. So a large global index might reintroduce problems that a large relation already have, like slower vacuum, slower maintenance, slower indexing, because you have a big index relation instead of multiple small ones. So that's where the contradiction comes from, and I believe also the community discussion, that's the main problem with this approach. So we'll talk about our approach to address this later. So our approach, and this is where the terminology kind of differs a little bit. So in the community, it's called global index. That's a very general term. And it doesn't really target the uniqueness part. It actually comes with it because you put everything together, it's automatically globally unique. But in our approach, we want to keep the same partition structure like before, what Postgres already has. So it's like a one index relation per partition, okay? And we focus on adding logic to achieve the global uniqueness feature without touching the architecture. So we don't want to change this picture right here. We want to stay as it is. But on top of that, we want to add some application logic to achieve global uniqueness. So therefore, we kind of give it a name, global unique index. Again, this is just, we named it, but we can change this to something else later, right? So it's just to have an emphasis on the unique part. So when we have a global unique index, that means it's our approach. Without that is the original approach. So that's the way I interpret that. So just like I said, we just add new logic to achieve the global uniqueness. So you can say architecturally, they both are the same, but except one can do global uniqueness check, the other cannot. Okay. So we added a syntax here, global clause, that can be used in conjunction with create unique index on a partitioned table, okay? So, so here's a little example here. So you can create your partition like you normally would do, and then you can add some, insert some values into your partition table. And when you want to create a unique index, you can put a global clause here along with the unique. And keep in mind that I'm using the B, the column B, which is not a partition key. Partition key is A. So when I do that, it's saying, hey, I want to create a global unique index on this table. And you'll get an error right here saying, hey, B is duplicated because B is present in partition 1 and partition 2. So this is the simple example of a global unique index in action when you want to create one of these, okay? And without global, just like I said, without global, the clause, you are creating a regular index like the PG normally have. So in here, I don't have a global clause, but I still getting error because it requires me to include column A, which is a partition column, in order to create a unique index. And again, this kind of makes you must have a multi-column index. So that kind of affect the query lookup later. So with the global index, global unique index, I don't have the column A here. So this will result in an increased query performance. So I'll show you the numbers later. So that's the clause, the syntax for using this feature. So once you have a global clause and you create a global unique index, we give it a new Relkind, denoted with a lowercase g, to indicate that, hey, this is a global unique index, not a regular index. So regular index will have a Relkind of lowercase I, and we want to change it to G. And that's our indication to, or I should say the trigger to go through the logic, the new logic that we'll be adding for the uniqueness check globally. And as you notice, it's still a capital I here in the partition table. So that's okay. There's no data actually being stored in your, what they can call this a parent table or a partition table. The actual data resides in individual children's, if you want to call this, or individual partitions. Okay, so let's talk about how it works with create. Okay, when you create a unique index in a regular table, it requires a heap scan. It has to scan all the tuples into something called a spool structure. Okay, so a spool structure, you can understand it as just a memory buffer where to put your tuples. And based on the index here, we want to perform some sorting. So you see the diagram here. So first we're gonna scan that your relation, the actual tables. Scan all the tuples and kind of put it in the spools first, and then we do sorting on the spools. So the uniqueness check happens during the sorting part. Well, that kind of makes sense because if you're sorting, you wanna have them in the order. But if you see something that's repeated twice, that's a uniqueness violation. So if everything passes, and you actually go to the build process. So basically building out your B tree in order. So that's how the index lookup works. They have to be sorted, and then each tuple have to have an index tuple associated with it, and then that has a TID, and then you can look up faster. So this approach is okay, and this is repeated per partition. So you have a partition table, have 6 partitions, you will do this 6 times. And each run is independent of others. So that's why it cannot guarantee cross-partition uniqueness because everything is individual. The spools, you put it there, you sort it, and you destroy it before you go on to the next partition. So that's how it works right now. And let's talk about a global unique index. So if we know the sorting is where uniqueness happens, then the idea is very simple. If that spool contains everything, then we give it a sorting, and does that mean we have a global uniqueness guarantee? The answer is yes, and that's actually exactly the approach right here. So instead of having just your normal spool, we actually maintain a separate spool structure that is at a global scale, so which means it will live until you have finished scanning and finishing all the partitions. So the lifetime is longer than the before. And at the last partition, so this is where logic comes in, we have to know when is the last. When is the last partition? So because we have to do the sorting at the last partition. So you have to be absolutely sure that after this, there's no more partition to scan. So lastly, we will just do a scan, and then there you go. That's a global uniqueness guarantee right here. And after that, we can just throw it away. So in here, we don't build, right? We just here to verify the uniqueness. We're not actually building. So the build process is still follow the original process. But here comes a problem. How much data can the spool structure hold? And what happens in parallel if we do this in parallel? So that's the question here. So that's the circle one is the new structure we added. So size of the spool, Actually, there's a configuration parameter for that. It's called the maintenance work man, and it's default as 64 megabyte. So once it's full, it will switch to something called a tape-based sorting. So you can imagine tape-based sorting is to have to do this in different chunks. So when it gets full, so I have a little illustration right here. So you save spores, and when it becomes full, you sort it right there, and then you kind of save in the temporary file. And then you will do this continuously until all your relations have been finished scanning. So which means you will have temporary files at this time. So you will have a file contains the result of the last 64 bytes of sorted version. And in the end, it kind of collect all of them and do a merge sort from those temporary files. So the size is not an issue, but it's just that you will be using the temporary files, so it's the extra I/O there. It's a little bit slower, but actually that's how PG works right now. So we're kind of reusing what PG already have. This is nothing new. This is just already the way it is. And the global unit index in parallel, it goes the same way. You also use the tape-based sorting. So kind of sort your result, put on a temporary file, and except that in the parallel case is the per worker. Each worker is doing the sorting at the same time, and then they put their result in a temporary file. And there's a leader process kind of in the end collects everybody's result and do the final merge sort. So that's just how the PG sorting works. So there's nothing new. So just to show you the size problem. Now the attach. So that was how create works. That's how create checks uniqueness. But if you want to attach new partition, well, you kind of have to do a little bit more work. And this is where another contradiction, another kind of argument raised, because attach is supposed to be fast. And right now it is indeed very fast. You just attach it, and there's not much to do. You just attach a new partition and call this partition 5. But if you have a global unique index, you cannot just attach, because you have to make sure the tuples in your new partition don't have a conflict with your existing ones. So this is where we have to reuse that spool and sort method that we just talked about during create to kind of put all these existing partitions in the spool and also scan the additional partition to be all together in a global spool, and then we do a final sort. So it has to follow the same process to determine if this partition is good to go. Okay, so, and we'll talk about the problem with this later. So you just to give you a simple idea how it works and what it does to check the uniqueness. And detach. Detach is relatively easy. It's actually the same as what PG currently has, except that when you detach a global unique index, we gotta change this Relkind from G back to I. And again, this is our indicator. When or should we go into the logic to check uniqueness? But since it's detached, it's no longer a requirement, so we gotta change this Relkind back to I, and it will just become like a regular index. It is like that because we didn't change the architecture, the way it's stored, so it's looking the same. So that's one good thing about it. Okay, insert and update. So this follows a very similar fashion. So right now, if you want to insert some data into a table with a unique index, it actually has to do a fetch first, trying to fetch if this table already have a same, or I should say a record with the same key exists. So you will do that to the table that you want to insert to. But in order to guarantee globally unique, you basically have to repeat that. And this is, again, it sounds very like a performance heavy thing, but it is indeed. But there's a way to optimize this, and I will share about that later. So you basically have to visit every single partition, trying to fetch the same key. And then only that, you can finally say, okay, this is globally unique, and then let's go on with the insert. Okay? Now let's talk about timings. Okay. So we talk about the create, attach, detach, and insert updates. And that's the 5 most common clauses we're using. So with a global unique index, As you can see, with a comparison to the regular index, is actually directly proportional to the number of partitions you have. And this test is based on this query on the right-hand side, where I have a 6 partition table, each with 1 million records in there. So they all have the same number. And it actually takes about 6 times longer to finish the insert. And that kind of makes sense because for one partition, it takes 26,000 milliseconds to insert. But because we have to check the other partitions times 6, and you get somewhere about 156,000 milliseconds. So it's directly proportional. And that's in the case where you have to visit every single other partitions. And the optimization we'll talk about later to kind of make it a little bit faster. And delete roughly takes the same time, around 66,000 something. And the create, again, is a little bit slower too, about 1 second longer for this 6 million record case. And I think that's mainly because we introduced the additional spool, is extra sorting is being done. And so that's the where the drop in performance happens in order to guarantee that. And attach, again, is also 6 times longer because attach, just like I said, it has to visit, kind of scan every single partition. Again, do this for the number of partitions. Every time I have to do the scanning and sorting again. So the attach also has a little bit drop in performance. Actually, not a little bit, just proportional to number of partitions. And the detach is all the same. It's just no change in there. Okay, now let's look at the select. I was saying that because we removed the requirement to include the partition key, so right now you just have a single index key. And in that case, with the performance benchmarking with about 800 million records, 1,200 partitions, and we're just doing a select. And you will see under the partition table, the performance of the global unique index is significantly faster than in the case where you have no indexes. Of course, no index, very slow. But with the unique index regular, where you have a multi-colon index keys as a requirement, and that kind of bring down the performance quite a lot too. So it's like not even 1 TPS. But if you have just one index key, it's actually significantly faster. So the chart actually is supposed to have 3 bars, blue, green, and gray. But because the difference is so high, you only see the gray, and gray bar is a global unique index. And I also have some number here. That's the number with a regular relation. Of course, regular relation is one relation super fast with the index. So the number is absolutely crazy, right? But with the no index, it's super slow, right? So that's the select only number. And we also have a select plus update. So we know the update and insert is slower because they have to visit fetch from other partitions. So why not just mix them a little bit with the select? And in that case, we also have, well, I wouldn't say good. It's not as good as the select only, but we do have, in comparison to the regular unique index and no index case, is still significantly faster. So really, what we want to compete with is this guy, unique index, AID plus BID. We want to make sure this is better than that. We're not trying to compete with your single index, single relation index. Of course, it's very fast because when you start to have partitions, the performance will degrade the more partitions you have. So 200 is quite a big extreme case, and still we have better performance than the regular unique index part. So this select is using the where clause, where you put the BID or your unique global unique index as a lookup P. Okay, so it's not like a select star. It's actually a targeted select. So I should make that clear before I go into the numbers. Okay, so just a little summary on this impact here. So insert and attach have the most performance degradation, and we know why, because that's you have to visit so many partitions, and it's indeed directly proportional to your partition numbers. And the create is about 35% slower. But again, this is just based on my single timing case. It's not the average, so just a very rough idea. because when you do this multiple times, different case, maybe the number will differ. So right now, I'm just giving from my example to give you a number, some initial ideas. It's not the way you may change it once we have the optimization added, right? Delete and detach are roughly the same as with or without the global unique index. And the select, and as you can see from previous slide, it is a multiple magnitude faster than the traditional unique index due to the removal of the partition keys. We know it's that because we didn't change the architecture. We basically take that out. And even without the uniqueness check, it's still faster when you take the partition key limitation out of the picture, right? Okay, so let's talk about ways to improve. So we know insert is slow because it visits every single other partitions to try to fetch a duplicate. So I think where there's a discussion on the community, hey, we can optimize this if we can reduce the number of partitions to visit. That makes sense, but how can we do that? And we know that partition, it uses the partition key to split up the data. So he said that if we can maintain the max and min value mapping per partition, and that's your global unique index. So if you know the bound of other partition where the minimum and the maximum value of that global unique index key, and you know the one that you want to insert. So you can check if it's within the bound or out of bound. If it is out of the bound, then you are 100% sure it's not there because my number is not in your range, so you must not have this number. But if it's within the bound, then maybe yes, you have to check if it is really there or not. So potentially you can save a few trips to visit other partitions if you can maintain a max and min value of that global unique index, the index key. Just an idea, we haven't tried this yet, but sounds like a promising way to improve inserts. And there's another problem with inserts. You see concurrent inserts. So when multiple people trying to insert into, well, do the insert on maybe a different partition, but within the same partition table. And this is where the locking becomes a problem. So when we try to fetch the unique, the same value from other partitions, we actually use the lowest possible key. It's called access share lock. So it doesn't really prevent concurrent inserts. But when you have this lock for fetching, for reading, other backend can still insert to that. So you may be wondering, hey, what if I just finished checking and then you insert a duplicate right away after I just checked? Okay, in the insert case, it's okay because other people, the backend B, when he does an insert, let's say he insert a duplicate, he still needs to check every single partition. So it's like everybody doing the same thing. So they are cross-check always. So you will also see that a duplicate is in partition 1. So in that case, backend B will still fail because your backend A is in the middle of insertion, and because it sees that backend A is in the middle of inserting a value to partition 1, it will actually wait there and trigger something called a transaction level lock when it fetch a duplicate because it does not know if backend A will eventually commit or abort. So when backend B sees a duplicate inserted by backend A and it's not done yet, you actually wait here to wait for it to commit or to abort before it can declare if that's a duplicate or not once it fetch a duplicate. So it's a little smarter. Actually, this is the existing logic of PG, so it's nothing new so far. So you actually wait here for A to commit or abort, okay? But that comes to another problem. If both backend A and B fetch each other's duplicate at the same time and trigger a transaction level lock at the same time, and you will have something called a deadlock case. So you will have a deadlock occur in this case when both backend A and B fetch and discover the other backend's duplicate at the same time and trigger the transaction lock. So waiting each other, forming a loop. So that's where the PG will detect the deadlock and abort one of the transactions. Okay, so that's an issue with the insert when you have a concurrent insertion. And for attached, again, similar problem with locks, because attached has to do a little bit more work. It has to scan all the existing partitions and do the sorting. So it actually, in this case, you put a share lock in there. And the share lock is a little bit stronger than the access share lock. So which means when attached acquires a share lock, your insertion will wait. You will not insert when attached is in progress, okay? So that creates a problem because attach is supposed to be very fast, and when you are locking my tables, it prevent my concurrent inserts. And likewise, if there's a concurrent insert already happening into one of the partition, the attach has to wait now because attach need to acquire lock, but there's somebody inserting, so you have to wait for the insertion to finish. So again, this creates a problem because the attach probably will never finish if the insert is always there. It will just keep there trying to acquire locks. So that's the problem with attach because it's trying to do more work now and it needs lock to ensure it's fine. So yeah, so that kind of limits the flexibility of attach. But it's not the end of the world. There's potential ways to solve this. So here it is. So in PG, there's a feature called create index concurrently. I have not looked at the detail of create index concurrent, and I think there's a thread talking about having that supported in the partition table as well. And again, I haven't looked at the detail, but it actually separates the concurrency into multiple stages, okay? So which means in the end, you want to achieve that while you are doing a create index concurrently, it does not block your concurrent inserts, okay? So we try not to block the concurrent insert. That's what this concurrently is really doing in the current Postgres create index clause. So attach is very similar to this. Attach, so we are actually proposing that we can maybe perhaps reusing create index concurrently, the idea behind that, and move it to attach. So we can have a clause like attach partition concurrently or something like that. So when you have it concurrently with attach, then we know, okay, we're gonna go through the concurrency mode, which means you cannot just simply acquire a share lock. You probably have to, you don't need to acquire a share lock because you don't wanna block other people. So you have to do a little bit differently in multiple stages. And in the end, you still make sure I have everything covered and not blocking all the inserts. So again, this is just an idea. It's not there yet. It's just something that we're looking into, and maybe we can find something useful from the concurrency logic and apply it to attach. So that's something we're looking at right now. And actually, there's an email thread right here talking about create index concurrency support on partition table. I think it was not supported before, but this is something, I'm not sure if it's committed yet, but there's people discussing that. And that's actually where we are evaluating if that can be used to attach as well. Okay, just a little summary here. The good, cross-partition uniqueness guarantee. Of course, that's the main point. And we have an increase in select performance. Yes, that's great because we no longer need to include the partition key. So yeah, that's the third point. We don't need to include the partition keys. And again, the good is no architecture changes on partition table, optimizer, and planner. So that's a good thing. But I think the attach kind of, well, it's not architecture change, but kind of breaks a little the way the partition attach works because it's do more work. But again, this is something that you kind of have to do it if you want to have a global unique. So it's like no escaping this. And the bad, insert attach are slow with more number of partitions. And again, there's room for optimization. And right now we do have a patch sent out in the email thread. It's the unoptimized version, so it's still slow as it is. But again, it depends on use case. If your use case is just a few partitions, then maybe it's okay. But if you have a lot, then maybe it's not okay. And again, the locking problem for attach, kind of have to fight with the inserts. So that's the locking problem where we talk about we're using a concurrently logic, maybe we can solve that. And the deadlock, again, this is something that could happen with inserts with certain timing, but again, it's something that we will also look into with our team when we go back to this maybe later this year. And here's some related links. This is where the original global index thread was posted, and actually took me a long time to give it a read. And I think the main problem with the original approach is the fact that everything is in one place. So can you imagine doing a vacuum on a single partition? Yeah, and this is the big table, and your single partition, the one you want to vacuum is only maybe a portion of the big thing. Then you want the vacuum to scan everything, or maybe there's a way to identify that. So that's, adds more complexity there. So imagine all the maintenance and re-indexing. Can you re-index? So you have a big thing. Do you want to change just the portion that affects your partition? So that kind of architecturally makes it more difficult to maintenance. But it does have some benefit, but that's the problem. But again, I'm sure there are people discussing ways to resolve that too, but probably a long time ago, maybe it's not up to date yet. And this is our discussion on global unique index. So I'll upload this to the PGCon website, so you can give it a look if you are interested in. And these are some of the blogs I write about how it works and the performance and how to do benchmarking and potential ways to improve. I think that's it for today. And I'm open to questions. If I can answer, that's great. But if not, you can email me at cary.huang@haiku.ca. Yeah.
Yeah. So for now, this is only for B3, right?
Yeah. Right now we do it on B3 index,
Okay, yeah.
but it has possibility to insert others. But again, we use B3 as a starting point to get the community's feedbacks and to see possible ways to resolve some of the issues that I mentioned. But after that, we can talk about others, right?
Because the question that I'm leading to is, you are currently storing another spool with all the tuples.
Yeah.
Can't you use the resulting indexes that you just built and merge sort those and use that as a uniqueness check so that you don't have the overhead of storing?
Yeah, that's a possibility, but we didn't go that way because the way it is set up right now is that it's every scan or every build of the partition is clean. So it will get destroyed at the end and then go to next and start a new one. So we fear that if I make their lifetime longer, and we'll change the architecture of that.
I mean, you use normal BC indexes as the basis.
Yes.
And then after you build all the indexes on the partitions, those are unique. And then you do an ordered index scan on those partitions because it's BC that is very cheap.
Oh, I see what you mean. So you do it after everything's built.
Yes.
That's an interesting idea. Maybe that can work too. Yes. Yeah, there's ways to do this. We do it while we are building, but I think we can definitely try after that. After everything's built, okay, you're gonna do a scanning.
Have you thought about using the bloom filter?
Sorry, what's that?
Have you thought about using the bloom filter?
Bloom filter.
Yeah.
No.
Well, that might work.
That might work. Okay, noted. So yeah, just.
I think of the amount of data that might be problematic. We run problems with the you have to cite the right side of the filter, but it's been done before in systems like rocks too big.
Yeah, there's a lot of ways to.
And that would.
I should come over here.
Yeah.
Yeah, again, you can visit the discussion link and just shout out things in there.
Okay.
Because it's still open. There's still many ways to do certain things, and we just kind of get started our ways. Not perfect, we understand that, and that's why I'm here to tell you about the problems we are facing and potential ways we can resolve that. Because a lot of people are asking this feature, and yeah, that's kind of a controversial feature. But again, we try not to, not to be, changing the architecture too much, because there's a reason partition exists, right? So we want to, use logic to resolve the deficiencies the original proposal has, right? So that's the main point. I'm here to share the problems, and hopefully we'll get back to this one day. And if you can, shout out your ideas, feel free. Yeah. Okay, any other questions? All right. If there's no questions, that will be it for today. And thank you. Thank you so much. Thank you so much.